The closest star to Earth is our Sun. Thankfully, it's not in danger of exploding. However, if the Sun were about 8 times more massive, its story would end quite differently. It would explode in a spectacular event known as a supernova. Supernovae are among the most powerful explosions in the universe. To understand their scale, imagine holding a hydrogen bomb right up to your eye and setting it off. That would still be 1 billion times dimmer than watching a supernova from Earth. That's how intense these explosions are. When one occurs in a distant galaxy, it can outshine the entire galaxy's worth of stars, hundreds of billions of them combined. These explosions are so bright and sudden that they can seem to appear out of nowhere. Back on October 8, 1604, the astronomer Johannes Kepler looked up and noticed a dazzling new star in the night sky. It was brighter than anything else around it, almost as luminous as the planet Jupiter. On dark moonless nights, its light was strong enough to cast shadows. Fascinated by this mysterious object, Kepler recorded his findings in a book titled De Stella Nova, which means about a new star in Latin. He believed he was witnessing the birth of a star, but what he had actually seen was the violent death of one. The brilliant light from that explosion slowly faded over the course of about 18 months, eventually vanishing from view. Even after scientists figured out in the 1930s that these were not new stars being born, but massive ones dying, the name supernova stuck. Today, we know that stars between 8 and 30 times the mass of our Sun end their lives in these incredible explosions. But the way a star dies is not as simple as just blowing up one day. In reality, a star spends most of its life in a careful balance. At its core, it fuses light elements, starting with hydrogen, into heavier ones like helium. This fusion process releases energy, which pushes outward and keeps the star from collapsing under its own gravity. In a way, stars are held up by the very light and energy they produce. When the fusion process slows down, the core begins to lose pressure. Gravity starts to take over, pulling the star inward and compressing it. This compression raises the core's temperature, which in turn reignites fusion at a faster rate. This feedback loop keeps the star stable for most of its life. However, the star's fuel isn't unlimited. Over time, it begins to run out. Take our Sun, for instance. It's about 5 billion years into its roughly 10 billion year lifespan. Larger stars, despite having more fuel, burn through it much faster. A star with 20 times the mass of the Sun will only live for about 10 million years. The bigger the star, the shorter and more intense its life. For around 90% of its existence, a star's core is only hot enough to turn hydrogen into helium. When the hydrogen is depleted, fusion slows down again, and the core contracts, heating up to around 200 million degrees. At this point, helium atoms start fusing into carbon. This helium burning phase lasts for about 1 million years, but eventually the helium runs out too, and the cycle repeats.
The next stages of a massive star's life happen in increasingly shorter bursts. As the core compresses and heats again, carbon begins fusing into neon. This process only lasts about 1,000 years. After that, neon fuses into oxygen, which burns for just a few years. Then oxygen is turned into silicon, a stage that may last only a few months. Each new fuel burns faster than the last, and with every step, the star becomes more unstable. Eventually, it reaches a point where it can no longer hold itself together, and that's when the supernova erupts. As a massive star reaches the final stages of its life, its core temperature can climb as high as 2.5 billion degrees Celsius. At this point, silicon atoms begin fusing into heavier elements, mainly nickel, which quickly breaks down into iron. And that's where the chain of fusion stops. Unlike the earlier stages where fusion releases energy, fusing iron actually consumes energy rather than producing it. Iron is incredibly stable. It's like a dead end for fusion reactions. You can't gain energy by fusing it into something heavier or splitting it into something lighter. So once a star's core is mostly iron, the process that had been pushing outward and balancing the star's weight starts to slow down. The core keeps growing as gravity pulls more material inward, and the outer layers press down harder. Eventually, the iron core becomes so massive, about 1.4 times the mass of our Sun, that it hits a critical threshold known as the Chandrasekhar limit. At this point, gravity becomes unstoppable. The core can't hold itself up anymore, and that's when quantum physics steps in. Electrons in the core, which had been resisting gravity by their sheer motion, now run out of space to move. They get squeezed into the lowest energy levels possible. In that extreme pressure, electrons combine with protons in the atomic nuclei, transforming them into neutrons and releasing tiny particles called neutrinos. With the electrons gone, there's nothing left to push back against gravity, and the core collapses, fast. In a matter of seconds, that once massive iron core, which might have been 3,000 kilometers wide, is crushed into a dense ball of neutrons just 30 kilometers across. It becomes what we call a neutron star, an object so compact and heavy that a single teaspoon of it would weigh as much as a mountain. Meanwhile, the outer layers of the star, now unsupported, begin to fall inward too, slamming into the newly formed neutron core at nearly a quarter the speed of light. This impact creates a shockwave, but it's still not quite enough to cause the full explosion we recognize as a supernova. The real trigger comes from something you might not expect: neutrinos. These nearly massless particles usually pass right through matter like it's not even there. In fact, trillions of them are streaming through your body every second and you don't even notice. They're so ghostly that it would take a wall of solid lead a light year thick just to have a 50% chance of stopping one. But in the core of a collapsing star, things are different. The density is so extreme, about 10 trillion times denser than lead, that some of those neutrinos get trapped and transfer their energy into the star. This flood of neutrinos, estimated at around 10 to the 58th particles, becomes the key to unlocking the supernova explosion. Despite their tiny size and weak interactions, neutrinos unleash enough energy to tear the star apart. Yet, when the explosion happens, less than 0.01% of the energy is emitted as visible light, the part we can actually see. Even so, that light is powerful enough to shine brighter than an entire galaxy. Around 1% of the energy goes into flinging the star's material outward, but the vast majority of energy, over 99%, is carried away by neutrinos.
These neutrinos are actually the first messengers of a supernova. Because they travel ahead of the shockwave that produces light, they escape the dying star minutes or hours before any visible flash. This means that if we detect a sudden burst of neutrinos here on Earth, we can turn our telescopes to the right spot in the sky before the light from the explosion even arrives. Now, it's important to point out that not all massive stars end with a supernova. Some collapse directly into black holes, skipping the explosion entirely. There's also a second way supernovae can happen, when a white dwarf, a dense leftover core of a smaller star, pulls in matter from a nearby companion star. Once its mass crosses that Chandrasekhar limit of 1.4 times the Sun's mass, it becomes unstable and detonates. This is the type of supernova Johannes Kepler observed in 1604 from a star system 20,000 light-years away. Supernovae can also explain why neutron stars sometimes travel at incredible speeds. The explosion isn't always perfectly even. If one side blows out harder than the other, it can push the neutron star like a rocket. In fact, we've discovered neutron stars moving through space at speeds up to 1,600 kilometers per second, likely kicked out by an unbalanced blast. Even though our understanding of supernovae is relatively new, humans have been observing them for thousands of years. Ancient astronomers in India, China, the Arab world, and Europe all recorded these mysterious guest stars that would suddenly light up the sky. Still, supernovae are rare events. In a galaxy like our Milky Way, which has around 100 billion stars, only 1 or 2 go supernova every century. One of the most impressive examples occurred in 1054. When the light from a supernova 1,650 light-years away reached Earth, Chinese astronomers documented the bright new star. Today, if we look at that same spot in the sky, we see the Crab Nebula.
the glowing remains of that long-ago stellar explosion, still expanding and lighting up the darkness of space. Over the past 1,000 years, the aftermath of a powerful star explosion called a supernova has expanded into a cloud stretching across 11 light-years of space. These explosions don't just create stunning visuals in the sky, they also launch massive amounts of high-energy particles known as cosmic rays. These are mostly protons and helium nuclei, and they travel through space at speeds close to that of light. Despite their tiny size, they carry an enormous punch of energy. So, how close would a supernova have to be to seriously affect life on Earth? The nearest stars beyond our sun are found in the Alpha Centauri system, about 4.4 light-years away. While that might seem far, stars are constantly moving. In fact, on average, a star passes within just 1 light-year of Earth roughly once every 500,000 years. Now, imagine one of those stars exploding as a supernova while that close. The sheer kinetic energy alone, without even considering radiation, could do serious damage. At that range, it's possible the force of the explosion could strip away Earth's atmosphere entirely. But the trouble doesn't end there. Supernovae are so hot and energetic that they can forge elements heavier than iron, something normal stars can't do. In the months following the explosion, these freshly created elements go through radioactive decay, releasing deadly gamma rays and more cosmic rays into space. Only a tiny fraction, less than 0.1% of a supernova's total energy comes out as gamma rays. But even that small amount is still dangerous if the explosion happens nearby. A supernova just a few light years away could bathe Earth in enough radiation to be lethal, although luckily our atmosphere, especially the ozone layer, does block much of that radiation. However, those cosmic rays pose another serious threat. When they crash into our atmosphere, they can split nitrogen molecules, which in turn react with oxygen to create compounds that break down ozone. If too much ozone is destroyed, harmful radiation from the sun, like ultraviolet rays, can reach the surface unchecked, posing a risk to all life. We actually have evidence that past supernovae have affected our planet. Scientists have found increased levels of nitrates, NO3, in the atmosphere, which seem to match the timing of ancient supernova events. Now, supernovae happening within 30 light-years of Earth are extremely rare, maybe once every 1.5 billion years. But new research suggests that dangerous effects from a supernova could extend as far as 150 light-years, which would make these events significantly more common. In fact, there's evidence that one such supernova occurred just 2.6 million years ago, about 150 light-years from Earth. Back then, early human ancestors like Australopithecus may have seen it as a brilliant new light in the sky. We know this event happened because of something remarkable scientists discovered buried deep under the ocean.
In layers of Pacific Ocean sediment, researchers found traces of a rare form of iron called iron-60. This isotope has 4 more neutrons than the iron we usually find on Earth, and it's incredibly hard to create. Our sun doesn't make it, and it doesn't form anywhere naturally in the solar system. It's made almost exclusively during supernova explosions. Iron-60 is also radioactive, with a half-life of 2.6 million years. That means half of it disappears every 2.6 million years. Since Earth is over 4.5 billion years old, any iron-60 that existed when our planet first formed would have long since decayed away. So if we're finding it now, it must have come from a recent nearby supernova. And that's not all. Scientists also found manganese-53, another radioactive element associated with supernovae, in the same ocean layer. Together, these findings provide solid proof that a powerful star exploded close to Earth not that long ago in cosmic terms, and its impact left a mark deep in the very crust of our planet. The supernova that exploded roughly 2.6 million years ago didn't wipe out life on Earth, but some scientists believe it may have played a role in a major extinction event that shows up in the fossil record from around the same time. This event, found at the boundary between the Pliocene and Pleistocene epochs, saw a sharp decline in marine biodiversity. About 1/3 of large ocean creatures disappeared. One idea is that radiation from the supernova, especially cosmic rays, slammed into Earth's atmosphere and produced muons. These are subatomic particles, similar to electrons, but over 200 times heavier. They can travel deep into the Earth and ocean, and after the supernova, the number of muons raining down on Earth would have skyrocketed, possibly up to 150 times the normal levels for many years. Larger animals would have been hit hardest, since muons penetrate deeply and deliver a higher radiation dose to bigger bodies. This might explain why the marine megafauna, the big sea animals, were disproportionately affected. Creatures living in shallower waters would have had less protection from this radiation, while those in deeper parts of the ocean were better shielded by the water and fared better during the extinction. There's more indirect evidence that supports the idea of recent nearby supernovae. When scientists look at the space between stars in our galaxy, they usually find about 1 million hydrogen atoms per cubic meter. That might not seem like much, but it's the typical density of interstellar space. Yet, in the region surrounding our solar system, spanning hundreds of light years, there are about 1,000 times fewer hydrogen atoms. It's as if something massive swept this area clean. In fact, our sun and planets currently drift through this vast, low-density region, often referred to as the local bubble. Many scientists think this vast empty region was carved out by a series of powerful supernova explosions, each one blasting material outward and pushing gas and dust away. But even supernovae pale in comparison to something even more extreme, gamma ray bursts, GRBs. These are among the most energetic explosions in the universe, and they were first discovered by accident. In the late 1960s, American Vela satellites, which were designed to monitor for secret nuclear tests, picked up a burst of gamma rays, not from Earth, but from deep space. The surprise discovery opened a whole new chapter in astrophysics. Today, we know of two main causes of gamma ray bursts. Some occur when two neutron stars, the dense cores left behind after supernovae, merge together. Others happen during the collapse of supermassive, fast-spinning stars in events known as hypernovae. These are at least 30 times the mass of our sun, and when they die, their collapse creates a blast up to 10 times stronger than a normal supernova, often leaving behind a black hole. Unlike supernovae, hypernovae focus most of their energy into narrow, powerful beams of gamma rays, just a few degrees wide. If one of these beams were aimed directly at Earth from within 6,000 light years, it could blast away a significant part of our ozone layer, exposing the planet's surface to harmful ultraviolet radiation. That distance might sound far, but within that radius are hundreds of millions of stars, meaning we are far from safe.
One particularly intense gamma ray burst was observed on October 9, 2022. It was so powerful that it affected Earth's ionosphere, the part of our atmosphere that reflects radio waves, similar to the way solar flares do. And yet, this explosion happened 2.5 billion light years away in another galaxy, showing just how extreme these bursts can be. Some scientists even believe that a gamma ray burst might have caused the late Ordovician mass extinction, which wiped out about 85% of marine life around 440 million years ago. There's no solid proof, but GRBs are common enough in the universe that researchers estimate there has been about a 50% chance of Earth being hit by an extinction-level gamma ray burst in the last 500 million years. So if a nearby star were to explode as a supernova, or worse, a hypernova today, the effects could be catastrophic for life on Earth. But ironically, these same cosmic disasters may have made life here possible in the first place. Around 4.6 billion years ago, long before Earth existed, a nearby supernova likely sent a shockwave into a cloud of gas and dust in space. That ripple may have triggered the collapse of the cloud, leading to the formation of our sun and solar system. Without that explosion, our planet and everything on it might never have come into being. So while these cosmic blasts carry the power to end worlds, they also carry the potential to create them. It's a reminder that in the universe, destruction and creation are often part of the same process. And while watching a video can help you get a general idea of how all this works, truly understanding it means digging deeper,
asking questions, exploring the concepts interactively, and building your knowledge from the ground up. The universe is full of incredible events, from the quiet deaths of stars to the explosive power of supernovae and gamma-ray bursts that can both threaten and create life. These cosmic explosions have shaped our world, and understanding them helps us see just how connected we are to the stars above. If you enjoyed learning about how these amazing space events impact us and our planet, make sure to hit the like button and subscribe for more videos that dive deep into the wonders of the universe. Your support helps me bring you more fascinating science in simple, easy-to-understand ways. Thanks for watching, and stay curious.